Okay, today we keep talking about buffer overflow. We will spend maybe 2 weeks on this. No, three weeks on this. So last class we talked about the brief history of buffer overflow, what information say functions need to run. We talk about two different, calling conventions on two different architectures. Also, we had several examples about overflowing local variables. In the homework, you had several challenges to overflow the local variables. So today we will do something even more interesting than overflowing the local variables. We will overflow the return address on the stack. Today we will say how can we overflow the return address to execute arbitrary function in the address space. We will also say how we can overflow the return addresses and execute many functions and also execute functions with parameters. So this is your first control flow hijacking attack. So last week, you overflow a local variable, but you didn't hijack any control flow of the program. The program was still running in legit control flow. It's just the data flow was changed. The data was changed. So today will be the first one we hijack control flow, and soon you will understand what do I mean by that. So on a function's stack frame, there are many useful information. We say that we will save the old EBP or 64 versions of RBP onto the stack, and that usually is called a frame pointer. The frame pointer, the frame base itself is data, okay? So that's a data pointer. However, we also save a return address there. So the return address is basically for a call function, a call instruction. The next instruction next to the call instruction, we will, when a function returns, we will go back there. And that address we need to save onto the stack. So we can call it the saved EIP or RIP. And because that address points to some code, we also call that pointer a code pointer. So both of them are stored on a stack. And because they are on the stack, it's very possible that if there's a bug, then those information will be overwritten. So in stack-based buffer overflow in general, the attacker's goal is to overwrite the saved return address on the stack, but not necessarily just directly overwrite the return address. It can also overwrite a saved EBP, a data pointer. The data pointer points to the previous function's frame. And in that previous function frame, there is also a return address. Right? So this is the most common vulnerability in C and C++ programs. The attacker's goal is to change the return value, then point it to the attacker's code. Then the program, when it returns, it will start executing the attacker's code. So the attacker achieves arbitrary code execution there. So let's look at a very simple example. This is the very first return address overflow example we have. I call it overflow return 1. Very simple function. There is a main function. The main function first print out the address of the print flag function. The print flag is a library function. It is already in the address space of this process, even though I didn't include it here. It's in another file. Then the main function calls valfoo. The valfoo function has a local variable at a C code level. It has 6 bytes. but the compiler may give it much more bytes. It's very possible. The compiler may decide to align different memory variables to make the accessing of them faster, but at a C code level, it's only 6 bytes. Then there is a C library function gets. Well, this is very similar to string copy, fread, those kind of functions. So it's basically the C library function to get input from the std in. So I used many different functions here to show you that there are many vulnerable functions or unsafe functions, not just the string copy. So the gets will get some input from std in. So when we run this program in the terminal, the standard input is just the terminal. Then put whatever you input into the buffer. So you can say there is a buffer overflow problem because you may input a very long string there, which will overwrite buff. Then the valve just return. After the valve return, the program will print IPT the full. Okay? So if you just run this program, we go to our. Let me talk a little bit more about gets. So gets will read one line from the standard input into the buffer pointed by the parameter until it reaches a new line, end of file, or 0 byte there, a null byte there. So there is no checking for if there is a buffer overflow, same as string copy or fread. So this is an unsafe function, and you should not use this function anymore when you program. Actually, the latest compilers, if you use this function, the compiler will give you a warning. Those functions are not safe. So let's take a look. Let's run this program. Overflow return 1. Let's do the 32-bit. So when we run this program, it will print out where is the function address for print flag. Then it asks for some input. Then if we just input something shorter than 6 bytes, nothing will happen. It will just print out IPT the full. But if you input something very long, you will trigger a segment fault, right? So many of you, when you program in C, especially under Linux or Unix, you are familiar with this segment fault. But today we are going to look at what exactly is a segment fault and how we can exploit this bug. So this is a disassembly of this valve. On the left-hand side, I have the disassembly. Right-hand side, I have the stack. Let's assume we are just calling into valve from the main function. So before we execute the very first function in valve, the stack pointer ESP should point to the return address on the stack. And the return address is actually in the main function. So this is what the stack looks like now. We don't really care about anything higher than that or anything has a lower address than that right now. Then the first instruction we get executed here is UndBR32. That's actually a security feature. Some of the new CPUs can use this instruction. Older CPUs will just ignore this instruction. So for today's class, we will just simply ignore this instruction. It doesn't do anything. Let's say it doesn't do anything. Then the second instruction will be the traditional function prologue. We have a push EBP there. So after we execute push EBP, then the value in EBP will be saved onto the stack. So ESP moves down 4 bytes. The saved EBP will be on the stack. And the saved EBP actually points to the stack frame of the main function. After that, we have move ESP to EBP, which means now both ESP and EBP point to the old or saved EBP onto the stack. Then we have a subtract 18 in hex, which is 24 bytes from the ESP. So now ESP will have a lower value than EBP, and the distance between where ESP points to and where EBP points to will be 24 bytes. After that, we subtract ESP again. Okay, you may ask why the compiler is doing this. It's just because the compiler didn't go through enough layers of optimization. Obviously, for a smarter compiler, we can merge this into just the one instruction. But the code you guys are looking at running on our system will be something like this. Then after this, we know the effective address, EBP minus E to EAX. So now EAX also is a pointer. Inside EAX, it's a value of EBP minus E. So it's in the middle of the first 24 bytes we reserved there. After that, we push EAX. So when we have a push, something like this, it's probably to set up the function call. So after that, ESP where points to somewhere here, it where points to the value we put into EAX, which is actually EBP minus E. And this is actually the address of the buffer we have there. Then we are going to make the function call gets. So gets only take one parameter, and that is what we pushed here. So you can say at a C code level, we ask for 6 bytes, right? We only say the buffer, we only need 6 bytes. But the real address for that buffer is at EBP minus E. E is 14. So between the beginning of the buffer to the saved EBP, there are 14 bytes. At C code level, we ask for 6 bytes, but the compiler actually give us 14 bytes there. After that, we're not going into the function gets. After we return from function gets, obviously we will keep executing here, and our ESP should be balanced. So after we execute the call, the ESP should still point here. The next instruction we have is add ESP by 16 bytes. So ESP moves up. Then we move 0 to EAX. That's for the return 0 in the C code. So when a function returns, EAX has a return value, and we're returning 0. So we move 0 to EAX. Then we have 2 more instructions. The first one is leave. Like I said at last class, leave is equivalent to 2 instructions. One is move EBP to ESP, then pop ESP. So the first instruction, move ESP to EBP to ESP, will make ESP and EBP have the same value again. And they have the value, they will point to the saved EBP on stack. Then after that, pop EBP. So pop EBP will just pop whatever ESP points to and move that value into EBP. So this is basically how we restore the saved EBP value. We restore the main function's stack frame address into EBP. Okay? So after this, we only have because this is a pop, ESP will move up 4 bytes. So ESP doesn't point to the return address anymore. And EBP will have whatever was stored here. Then after that, we are going to execute the return instruction. I have a little bit, okay, so this one I should move to here. Sorry about that. So the last instruction we are going to execute here is a return instruction. And the return instruction will pop whatever the ESP was pointed to EIP. Then ESP moves up 4 bytes. Then the CPU start executing at this return address. So how can we overwrite this return address? Like we overwrite everything else. We already know that the buffer is at EBP minus 14 bytes. So if we put 14 bytes of garbage there, we can fill that buffer. Then we put another 4 bytes of garbage there, then we can overwrite the saved EBP. Then we can have 4 more bytes to overwrite the return address. The return address used to be an address in the main function. Now we overwrite that to whatever we want. So here we want to overwrite to print secret because we want to print secret, right? So if we overwrite it this way, 14 bytes of garbage, another 14 bytes of garbage to overwrite the saved EBP, that's 18 bytes in total. Then another 4 bytes for the print secret function address. Then when this program executes to the point return, what happens is this print secret address, this should be print flag, will be popped into EIP. Then we keep running from a print flag. So that's how we can get the flag. So go back to the program here. Let's say so I think the best way to do this is we debug this program. Let's debug this program. We set a breakpoint at Overflow. Then so this one we are getting input from std in. Let's run this program first. Let's get the flag first. So when we run this program, as you can see, no matter how many times I run this program, the print flag function has the same address. Okay, this 6260, that's the same address. For modern OS we are using, no matter your laptop, your phone, actually if you run this program multiple times, the functions, they will have a different address. For the platform we are using here, we disabled that security feature, which is called address space layout randomization, which we'll talk about in a few weeks. Because we disabled that feature, this address will not change. We disable this because we want to make it a little bit easier in the beginning of the class. Later, there will be a challenge for you guys to bypass address space layout randomization. So we already know that we need to overwrite 14 bytes to this, right? Now, let's say we do a Python 2, say, so here we are inputting 14 bytes. Let me do an object dump to see if the battery is the same. So this version, actually, the battery is a little bit simpler than what I have in the slides. But you can see the buffer here is the same. It's the EBP minus E, which is 14 bytes. So when we do, oops, we are here. So when we try to input 13 says, which is a string, then it will the terminal will attach the 0 byte at the end, making the total length of the string. Well, in C language, the string is 13 bytes, but actually it takes 14 bytes of space because you always have a null byte, 0 byte at the end, right? So when we do this, we overwrite exactly what at the beginning of the buffer to the beginning of the saved EBP. So nothing critical. That's why when we do this, we do not trigger any error. However, if we do one more byte, like 14, what happens is the ending 0 will be put into the saved EBP, the least significant byte of saved EBP. If that byte was originally not 0, then we overwrite it with something. And because of that, it may trigger a segment fault, because that value eventually will be used when we return from this function to get the frame of the main function. If we change that, which means we cannot correctly get the stack frame of the main function. And because of that, eventually we will trigger a segment fault. So when we do this, you can say we get a segment fault. Okay. So obviously, if you have many more bytes, it will be the same thing. It actually may trigger the segment fault earlier, but it's not showing, by looking at the output, it's not showing when the segment fault is triggered. So our goal here is not to trigger the segment fault, but to get the flag, right? Like we said, what we do is we put 18 bytes here, because from the beginning of buffer to the beginning of saved EBP, that's 14 bytes. We are going to overwrite the saved EBP, which is 4 bytes, total 18 bytes. Then we are going to put the address of print flag here. So we have the 18 bytes of this. Then we put the address of print flag here, which is 60.62.55.56. So when we do this, when the val foo returns, it doesn't return to the main function. It returns print flag function, which print out the flag. However, we did overwrite the saved EBP here, which means the print flag function will not have a correct stack frame there. It doesn't have a stack frame on the stack anyway, in the first place. And because of that, eventually when the print flag function returns, it will return to a random address. We may not have anything at an address. That address may not be even mapped. And because of that, we trigger the segment fault. But before that, we already got the flag. Okay. So this is the very first version of overwriting return address. Any questions so far? Make sense? Okay, so let's move to the 64-bit version. It's actually very similar. The val foo looks different. The very first instruction, let me see if I have an animation here. Okay, I don't. So the very first instruction here is endbr64, like I said, like the endbr32. We ignore that for now. Then the second instruction is push RBP, then move RSP to RBP. Then we subtract something from the RSP to reserve some space for local variables. Then we load the effective address, RBP -6 to RAX. Then move RAX to RDI. So for 64-bit version, if you remember the calling convention we talked about a week ago, or maybe the first class. 64-bit version, we put parameters in the registers first. The first parameter is placed in the register RDI. So here we are actually setting up the parameter for the gets function, the 64-bit version of gets function. And we're not pushing to the stack anymore. We're actually using EDI. So as you can see here, in this version, the buffer is actually at RBP minus 6. The previous version was EBP minus E, okay? So compiler make different decisions. So here we ask for 6 bytes, and the compiler only gave us 6 bytes. The 32-bit version, we ask for 6 bytes, the compiler actually gave us much more. Then after that, we move 0 to EX, we call gets, then we move 0 to EX again, then we just leave and return. So to hack this one, obviously it's very similar to the previous one. Oh, should be return. Oh, here, return 1. So this one is very it's the same. It's just buffer size is different. Besides the buffer size is different, everything, the address size is also larger, right? So here we already know the buffer is 6 bytes. So we overwrite that 6 bytes. We put any garbage value here. I put Z here. Then 6 bytes of that. Then we should have how many bytes for what? We should have the saved RBP, right? So what is the size of saved RBP? So EBP was 4 bytes. That's a 32-bit machine. This is a 64-bit machine, so it will be 8 bytes. So which means here we need 14 bytes in total, 6 plus 8. Then we will have the return address. Oh, actually we haven't run the program yet. Let's run the program. So that's our address. So how long is this address? Also 8 bytes. So what we need is actually D6, 11, 40. That's the least significant bytes, 3 bytes. Then the higher 5 bytes are just zeros, right? So you need to put zeros there. So that's how you get the flag. Okay, let's do a test. What if I do not put those zeros here? What will happen? It's not going to work? Okay. So how many of you think this may work? Yeah. So some of you think this may work. But why would this work?
Because since you didn't set the first byte byte or the last byte byte to 0, it's still randomized in a sense. So
Yeah.
it's going to bring you to a different address if it's all there.
But what if it's not just some random value there? It's basically the value for the correct return address, right? But the correct return address may already have those zeros there, right? So it may work. Let's try. For this one, it actually works. Because you are supposed to return to some address at the main, and that higher 5 bytes actually is already 0. Okay. So your export can be a little bit shorter in this case. Let's say you are doing a remote attack. You save several bytes for your exports. Maybe that may be critical. So that is basically how we can overwrite the return address and jump to anywhere in the address space. So the function we just jump to or return to is called the print flag. And that function doesn't take any parameters. So can we jump to a function that take parameters? So that is basically overflow return to. And there are many different ways we can solve this challenge, actually. We are going to look at two ways. This function is almost the same as the previous one, except that the main function calls Overflow, except that we're not supposed to directly call print flag, okay? You can still do that. You can directly return to print flag. But the goal here is we want to return to the beginning of print secret instead. We do not directly return to print flag. The Overflow, the main function, they are the same. So the print secret function actually takes one parameter, and there has to be a specific value. And that is quite similar to the overflow local challenge you did last week. But here we only need to set up the parameter. We don't set up a local variable there. Then let's say how we can hack this one. It looks very simple, okay? It looks like you only need to overwrite one more local variable, but you need to figure out what's the address of that local variable or the parameter. And it's a little bit tricky here, actually. It's trickier than it looks like. It may look like very simple, but it's trickier. Let's say right now we are at the end of Overflow. And this is what the stack looks like. Let's move a little bit here. Okay, here. So this is before we call gets. We haven't overwrite anything yet. There is a buffer, there is saved EBP, there is return. Okay. Now when we do gets, we will be able to overwrite everything here. And what we're trying to do is we need to overwrite the return address. We already know that. And also, we cannot avoid overwriting the saved EBP. We don't really need to overwrite that. We don't want to overwrite that. But we cannot avoid overwriting that, because that is how gets or string copy works. They do a sequential copy. So if we want to overwrite the return address here, we have to overwrite this part, okay? So let's assume we put 4 letters A there, uppercase A, which has an ASCII value of maybe 61 in hex, maybe. Anyway, it's 4 bytes. We put 4 A's here. Then let's see how that 4 A's will be used here, okay? So now when we return, what we'll do is move EBP to ESP, then both EBP, ESP points to those 4 letters, A's. Then we pop EBP, which means whatever ESP points to will go to EBP. So now EBP will have the value 4 bytes of letter A's, okay? Then ESP moves up 4 bytes. ESP now points to the return address. Now we are going to return. So when we return, what happens is whatever ESP points to will go to EIP, right? So now EIP has the address of print secret. Okay, here we're actually using print secret. Okay, this one points to print secret. However, EBP has some garbage value we put there, 4 letter A's, 61 in hex, 4 bytes of that. Now we are going to the function print secret. Okay. So this is a So at the beginning of print secret, what we are going to do? There is another instruction, push EBP, move ESP to EBP, because this function will also set up its own frame. And by doing that, something interesting happens. EBP has a value of 4A's, and we push EBP, so whatever, so let's say, so what used to be the return address or the address of print secret will be overwritten to 4A's because EBP has that value. Then we move ESP to EBP, then both of them points to 4A's. So to the function print secret, it doesn't know there was a tag, right? It doesn't know it is executing because someone returned to it. It believes, or it is compiled this way, it is executing because someone calls it. And he believes, print secret function believes someone called me. And for that print secret function, it will treat this part, whatever EBP plus 4 points to, as a return address. Okay? And we didn't really put anything there. And because it will treat its own EBP plus 4 as a return address, it will treat EBP plus 8 as its parameter. Okay. So the stack will actually look like this. So when you overflow this, you actually need to, when you overflow this, you are overflowing from which function? You are overflowing from the Overflow function, and it has a buffer here. So you need to overflow from the buffer. You need to, you will have some, this part is the Overflow's saved EBP. The value doesn't matter, but that value will eventually also be copied 4 bytes higher because print secret will treat that as the saved EBP. Then 4 bytes higher will have a return address for print secret. If you want print secret to return again, in this case, we don't care. 4 bytes higher than that, we finally have the parameter, and this function only has one parameter, which is I here. So when you overwrite, you need to overwrite 2 different places. One is the return address for the Overflow. The second one is the parameter for print secret. And between them, actually, there are 4 bytes. Does this make sense? Okay, this part is a little bit trickier to understand. So after the class, I hope you can debug this and also look at the slides, look at the animation many times, and hopefully you can understand this part. So going back to the demo, which one? This Overflow return 2. So this is a program. When we run this program, it gives us the print secret address. If we want to return to print secret, so let's go back to the figure here. Do I have disassembly here? Okay, I don't have a disassembly here, so we need to disassemble this to see what is the size of the buffer. So let's look at a Overflow. This is a call to get. And the buffer's address is at EBP minus E14, which means we need 14 bytes of garbage first. we need 14 bytes of garbage, then 4 bytes of the old EBP for Overflow, so which means 18 bytes of garbage. Then we need the return address for print secret, which is, let's run this program to say the address. Which is 38, 63, 55, 56. Okay? So if we input this, we will successfully return to here. However, when we keep executing from here, then print secret will check if the parameter is this particular value. But we didn't set up that, right? So it's a random value. So there is just 1 out of 4 billion something chances we can get the flag. Instead, we are going to have 4 more bytes of garbage. So this is the tricky part, why we need 4 more bytes of garbage. That's what I explained to you just now. Then we have the value for I, which I believe is 67, 56, 34, and 12. We pipe this into this program. So this is how we get the flag. So let's say if we do not have this part, or we have a different value, so 78, we change to FF, it will say I pitied a fool because the value doesn't match. Or if we do not put this value there, the same thing, right? We do not get that. So this is what we need to do if we want to jump to the beginning of print secret. So like I said, if you just want to get a flag, another way is you just jump into the beginning of the function print flag. You don't have to jump into the function print secret. Or if there is another approach here, let's say we do not jump into the beginning of print secret, we do not jump into the beginning of print flag. Is there any other place we can jump to and we can still get the flag? And we do not need to set up that I. Let's say we bypass that, yeah.
Can you jump to the print flag call in print secret?
Exactly, right? Because you can jump anywhere in the address space. In the second half of the class, we are going to talk about something called return-oriented programming. In that one, you do not even need to jump into the beginning of a legit instruction. You can jump into a middle of instruction. The compiler will generate many instructions. The instructions may be 5 bytes, might be 7 bytes. And let's say that move instruction may be 4 bytes. If you jump to the beginning of that move instruction, that 4 bytes, then it's a move instruction. But if you jump to the middle of that, the CPU will interpret that as a different instruction, right? So here, we're not trying to do that. That's what we're going to do in the second half of the class. Not today's class, this semester's class. So the second way, like Alex said that, we can directly jump to here, okay? We do not jump to the beginning of this. We do not jump to the inside the print flag. We jump to the call to the print flag in the print secret, okay? So we just need to figure out the address of that. So we can debug this program. We set a breakpoint at Overflow. No, we set a breakpoint at, doesn't matter. We can set it anywhere. Okay. We set a breakpoint at the main function. We run this program. Now we just disassemble the print secret function. So now you see the disassembly of the print secret function, and you can see here, there is a function call inside print secret function, and this is the address. We copy this address. Then we overflow. Now, because we don't need to set I anymore. So this part we don't care. We can have it. It's not going to do anything. Then we only 4B 6355 56. So now we jump into the middle of print secret. And as you can see, we can still get the flag. Okay. The 64-bit version will be similar. I guess we can take the break later. Okay, so we just saw that we can override the return address and to return into another function, even though that function doesn't know it is being returned to, it believes it's being called to, but we will be able to execute the code there. We saw that we can execute, actually we can jump into or return into a function with parameters. And obviously, not only one parameter, even several parameters will be the same thing. You just place whatever you want to override on top of that. Okay, so this one, the print secret has two parameters, I and j, and they have some specific values. You just need to override it this way. Okay, so I will leave this as a homework for you guys. Let's say this is return 3. Okay, let's do something a little bit more interesting. So we saw we can return to a function. Can we return to many functions? You see that each function, they actually will treat the return address of the, they will consider their return address on the top of the stack, right? But their point of view of top of stack as moves 4 bytes. So the return addresses do not overlap. They don't overlap. So because of that, it's possible for us to chain many functions as long as they do not take parameters. Let's say this is the argument. This is a stack of val foo. The val foo at the bottom, there is a buffer, and between the buffer and the saved EBP, there is some room. Then there is saved EBP, and before this one returns, the EBP points to the register EBP points to the saved EBP, and now we have a return address that. If we overwrite that return address to the function address, F1's function address, then we can have something like this. Then we can have this. We actually can also have 2 arguments here, let's say. But those arguments are not F1's arguments. Okay. Anyway, this is something else we can overwrite. Okay. So after the val foo returns, ESP actually will point to this place, 8 bytes higher than the old EBP. Then we go to the function F1, right? Then when F1, at the beginning of F1 will treat this address, which is the previous function's EBP, will be 4 bytes higher. So this place will be treated as F1's saved EBP, and the return address will be, so F1 will think its return address will be 4 bytes higher. So because of this, we can actually chain many different functions together, like this. This is the only vulnerable function is vol_foo, okay? We only have one chance to overwrite the memory. F1, F2, F3 are just functions in the address space we want to return to. Then we can put F1's address at vol_foo's return address, we overwrite. 4 bytes higher, we put F2. 4 bytes higher, we put F3. Just as simple as that. We can chain function 1, 2, 3 together. After we return to F1, F1 executes. When F1 finishes executing, F1 returns F2. F2 executes. When it finishes, it returns F3. So we can actually chain different functions together. This is an example, overflow return chain. Okay, so the vol_foo is the same vol_foo. Main function, almost the same. It's just I print out the address for many different functions. The function we have here is F1, F2, tier F5. F1 print out knowledge, just one word. F2 print out is. F3 print out power. F4 France. F5 bacon. So at the end of F5, I call the C library function exit. That's a C library function, but eventually that library function make a system call which has the same name, exit, which means F5, that function will not return, okay? So if F5's stack is corrupted, if F5 doesn't have a valid return address on its stack, it doesn't matter because it doesn't return. It will directly kill the process. So the goal here is to print out the string, knowledge is power, and the France is bacon, okay? So we are going to print out is twice. We're going to return to the same function twice. Then let's see how we can do this. Chain 32. So we first run this program. We get the address of all the functions. Then it's actually simple from here. What is the first step? What's the first step here? Our goal is to overwrite the return address, right? We already know the value or the target we want to return to. But you still need to figure out how big is a buffer, right? So the first step is to say the disassembly of this program. We say the disassembly of the program. We look at the vol_foo. It's actually the same, still 14 bytes. Okay. So we will have 14 bytes of buffer, which means 18 bytes of garbage. So we have 18 bytes of garbage. After that 18 bytes of garbage, we can put the first function we want to return to, which is F1. So F1's address is 2D625556. Okay? So when we do this, it's supposed to return to the first function and print out knowledge, right? However, let's say when we do this, it doesn't print out the knowledge. You see? It doesn't print out knowledge. It should print out knowledge, but why it's not printing out knowledge? Let me show you a different one. Instead of returning to F1, if we return to F5, I guess uppercase doesn't matter, just for consistency. So F5, there's print and exit, okay? That's a difference. So when we return to F5, it actually print out bacon, all right? But when we return to F1, it didn't print out anything. Why is that? Yes, but why do you think we need exit or something like that? No, that's not the reason. So in print flag and everything else, we probably do not have an exit. So what happens here is it's close. Okay, the direction you are thinking is correct, but not exactly what happened. So what happens here is that printf function we have there is no like a /n, a new line, or an exit. So when you call the print, the first one, printf knowledge, the program actually put the string, will tell the kernel to print out the string knowledge. But because it's not a new line, the kernel will buffer that. The kernel will wait. The kernel will not print that out directly. The buffer will wait for more data, then print them out together. However, the program crashes before the kernel had a chance to really print that out. So that's why when we do that, directly return to F1, you do not really say that get printed out. Okay. The F5, there is an exit. That program will not crash. When you return to F5, it will not, let me say, will it crash? Yeah, no, it will not crash. As you can see that when we return to F5, it doesn't crash. It prints out bacon, then exit, the program exit gracefully. It doesn't crash because it makes the system call exit. Okay. So now we want to chain them together. We just need to put all their addresses here. F1 first. We will have 6 of those. 6 of those, so I just copy this. So that's 5. Need one more. Oops. So we want to return to F1 first, right? So which means we have 2D 6.2, 5.5, 5.6. Then we want to return to F2 for A. 6.2, 5.5, 5.6. Then 6.7, 6.2. 5, 6. So we are going to use F2, which is print out is again. So F2's address here again, 4A 62 55 56. So after that, the last one, A4 625556. Okay. I hope I didn't mistype. Let's try. Yeah, it works. Well, it's not perfect. There is a dot here. Oh, actually we want that period there. Okay, so see, now we return into those 5 functions in total 6 times, right? The first time we print out knowledge, then is power, then, okay, the order is wrong. It should be France is bacon. So, by the way, does anyone here know why France is bacon? You guys don't know this? Okay, you guys are too young, okay? So one of the homework today is just to Google this. Knowledge is power, France is bacon. It's a funny story, yeah. Okay, so that's how we chain multiple functions together. So technically, if those functions do not take parameters, we can chain unlimited numbers of them together. This works for 64-bit version as well. It's just a 64-bit version. The address is 8 bytes. So however, if the functions we want to return to, they take parameters, does this still work? Intuitively, you can feel this may not work, right? Because we put the return address one after another. And which means for some functions, their return address will have the same address as other functions' parameters. They have the same address. And you only have one shot to overwrite. So you cannot write 2 different values at the same address, right? Unless somehow the return address of a function and a parameter of another function, they happen to be the same. Otherwise, this will not work. I did see a paper talking about approach that you can use a similar approach to return to any function, any number of functions, and they have different parameters. But I don't remember how exactly it works. You probably use ROP, I think. That's a long time ago, so it's difficult to find that paper too, I guess. Okay. Okay, so let's take maybe 10 minutes break. When we come back, we will look at our first share code. Okay, let's resume. So the attack you just saw is fun. We are able to get the flag by returning to the print flag function. However, we're able to get the flag because in the address space of this program, there is already a print flag function. So, but if you try to hack any software in real world, obviously there will be no functions convenient like that, right? You hack a real world software, the software will not have a function called print flag. It will not have a function give me the secret, right? So, but we want to hack those functions. We even want to hack the whole system. So how do we do that? So the approach we're going to learn today and next Monday is something called share code injection or malicious code injection. So we do not only hijack the control flow, we also inject some malicious code into the address space. So in the original address space, they do not have the function we need, we inject one. Okay. Then we will talk about how do we defeat this kind of attack, maybe next week or the one after. Then in the second half of the semester, we are talking about even if the program or the OS doesn't allow you to inject your own malicious code, then how do we just use the pieces of instructions, pieces of garbage in the address space to wave some malicious programs. That is return-oriented programming, which is a very fun topic we'll talk about the second half of the semester. So today, let's start with injecting shellcode. So you already know that if the data you input there is big enough, you will be able to overwrite the return address. And you can overwrite that return address to wherever you want. However, the address space may not really have what we want. So this is the stack, what the stack looks like. If we, in the function of Overflow, it has a buffer, it has saved the EBP, has a return address. Before overwriting, the return address is valid. It's a legit return address. It's actually somewhere in the main function. So when we overwrite it, we overwrite the whole thing. We don't have to overwrite anything beyond this. Then this return address, for us, we can control what to overwrite, where we return to. So, however, the problem, like I said, is let's say there is no print flag there. There's no print flag function in the address space. We still want to print out the flag. So what do? Then we develop something called shellcode. So as the name suggests, shellcode technically refers to a piece of code that returns a shell to the attacker. The shell is like a command line interface. You can ask it to launch other programs. That's a shell. But right now, shellcode has more general meanings. It doesn't have to return a shell. It can do many other malicious things. We'll call them shellcode. So the shellcode, basically the shellcode, they are just several instructions, many instructions, usually not very long, hundreds of instructions, most of them just 20 or 30 instructions, that's it. Then they are basically, you compile them usually from assembly code, and you want to inject them into the address space of the process you are hacking. So let's say, look at this picture. For the Overflow example you just saw, we actually can put shellcode at the beginning of the buffer. So we used to put garbage there, right? We just put garbage there. We don't care what we put there. we can actually put share-code there, as long as the size is big enough. Or we can put share-code at a higher address as well, okay? Another problem is the share-code is cold, which means when you jump to that, you have to jump to the beginning of that. If you jump 1 byte off, if you jump 1 byte lower, or let's say, then there is 1 garbage byte. And because of that 1 garbage byte, your code will not execute successfully. Or you jump even just 1 byte higher, then you will jump into the middle of your first instruction. And that will also trigger segment fault. So there's a technique we use is in front of the share code, we put something called the NOP sled. NOP stands for no operations. Basically, they are valid instructions, but they don't do anything. For some architectures, there are specific instructions for NOP. For Intel, actually, there is a NOP instruction. That instruction doesn't do anything, but that is a legit instruction. So if you put, and that only takes 1 byte. So if you put a lot of NOP instructions, like NOP sled, at the beginning of the share code, you don't have to jump to the exact address of the share code. You just jump to the middle of the NOP. Then the NOP doesn't do anything, give the CPU control to the next instruction, eventually give the CPU control to your share code. Today we're not going to do this. Next week we're going to do this, but that's the high-level idea here. You can also put the share code at a higher address. Doesn't have to be a lower address, a buffer. Maybe the buffer is not big enough to do that. So next, what we do today is you will look at your very first share code. So this is a very simple share code. It only does one function, which is execute a shell. Okay? So this is literally a share code, return you a shell. However, this version doesn't really work on our platform anymore. So next week, we will talk about a little bit more complicated version. But this is a version that works for decades. For 20, 30 years, it worked. Only recently, on the new platform, on new Ubuntu, it doesn't work anymore. We just need to change this a little bit. But you need to understand this part first. So you actually already saw this. I don't remember last week or the first week. I showed you a little bit what this is. So this is 28 bytes of share code. So you can say how small it is. Only 28 bytes. Only those instructions. Only those numbers. And this can give you back a shell. So how do we generate this is we write the assembly code there, then we compile it, we get the share code. So I believe 2 weeks later, you will write some share code yourself. There will be some constraints, and you need to craft your share code to bypass those constraints. So the first instruction here we have is just explore EAX. We probably talked about this last week, right? So EAX, then after first instruction, EAX will have value 0. I think I have animation here. Here we have animation. So left-hand side, we have the instructions. So this is the assembly or disassembly. This is just the bytes. The raw bytes will look like this. You can get the share code from this link. And this website, they actually have all kinds of share code for different purposes. So let's try to understand those 28 bytes. Some of you probably use some tools like a meta exploit, something like that before, or anyone heard about that before? Yeah. So when you use those kind of tools, you just click buttons, and the meta exploit will send out those exploits or share code. So you do not really understand what they are sending. So in this class, we actually look at the lowest level of software security. I want you guys to understand what those tools are sending. So the first instruction here is exclusive OR EAX. So after this, the register EAX will have the value 0, right? Then we push EAX. EAX is 4 bytes. We push EAX, we push 4 bytes onto the stack. So the stack will look like this. There are 4 bytes, all zeros. And ESP where it points to this place, basically. Then after that, we push 2 more values there, each of them 4 bytes. This 2 different values, and they will be like this order. So the top is high, the right hand is high. So basically, it will be 6E, 69, 62, this. Okay, blah, blah, this. Then after that, ESP right now points to here. Then we move ESP to EBP. Now, basically, EBP also points to this place from this one. Sorry, it should be 2F62 because it should be from low address to high address. Okay. Then after that, we move EAX to ECX. So EAX is 0. So after we move, ECX will also be 0. Okay. Then we move EAX to EDX. So after we move, EDX will also be 0. Then after that, we move B to AL. So EAX is not 0 anymore because AL, which is the least significant byte of EAX, is B, which is 11 in decimal. Then we make the system call int 80. That's the system call. So before that, what we are doing was to set up the parameters for system calls. So that's the first system call we make here, and that system call is EXE-CVE. If you go to the system call number for Linux, for x86, you can say number 11, that's the system call EXE-CVE. And to make that system call, you need to put that system number in the register EAX. That's why we put 11 in here. Also, you need to put some parameters. The parameter here is not correct. That's why I have another figure, this one. You need to put other parameters in other registers. The parameters you need to give here is, first of all, the string of the program you want to execute. The address of the string, actually. Then you need to put the argument for that program. So this is like the command line argument. When you execute a program or when you launch a command in the terminal, the first argument that program says, a command line, the arg v0 will be the name of the program itself. The second one will be the first argument you give. Okay? So here, when you make the system call, you first need to give the name, the address of the name of the program. So in this case, is /bin sh, which is a shell. Then you need to give the command line arguments you want to give to the program. And the first one is still the name of the address. So it will be the address /bin /sh, the address of that again. Then the third argument is the environmental variable. You don't have to provide that. In this case, we don't provide that, so we just give a 0 byte and null bytes there. So that's how we make this EXE-CVE system call. So this piece of code actually has 3 more instructions, okay? As you can see, the first instruction is making EAX 0 again, then increase EAX. So what will be the value after that? What is the value of EAX? 1, right? Then make another system call, you see? So then let's go back to system call table. So you tell me what system call that is. That's just exit. Okay. Then why do we have it here? So the first system call you're making is EXE-CVE. EXE-CVE is supposed to replace the current process with a new process, right? So if you replace the current process with new process, then why do we need the last 3 instructions? We already replaced everything. Doesn't matter, right? Why? Just guess. Why? Exactly. So the EXE for some reason, it may not work. If that doesn't work, what happens is then you are going to execute some random bytes and your program will crash. If you are an attacker, you probably don't want the program to crash. So give the defenders an indicator that someone is attacking you, right? So you want to exit gracefully. That's why we make another system called exit 0 here. So these last 3 instructions are not necessarily to pull off the attack, technically. And that probably, I think that cost 5 bytes. So technically, this piece of shellcode can be only 23 bytes, very small. Then let's take a closer look at why we are pushing those 2 weird, hard-coded numbers. Remember, this is what we have on stack, 2F, 62, blah, blah, blah. So if you check the ASCII table of that, you will say those numbers we put there are actually slash being //sh. So that's almost the same as the program we want to execute, except that there are 2 slashes, right? So why there are 2 slashes? Or does that really matter? What? It's not. Okay. For many programming languages, the backward slash is an escape, but here it's actually not. So for Linux, 1 slash is the same as 2 slash or even 1,000 slash. It's the same thing. Let's go to our platform, just here. Let's say we want to go to root. This is how you go to the root folder, right? Or let's go to temp. Let's see if we have anything temp now. Let's say we go to user 84. Okay. So let's say if we want to enter this directory, we do cd this directory, right? But you probably don't know is the number of slashes doesn't really matter here. You can put many slashes. It still works. That's the same thing. Let me go back to the root, then do this again. Doesn't matter, okay? So for Linux, the slash number doesn't matter. And the reason we are doing here, using this is because of this, we can use a slash as kind of like a padding here. If we do not use that slash, this will be how many? This will be 7 bytes. Then it will not be very convenient. The reason is I forgot to mention one thing. Look at this piece of code. You notice one thing is there is no 0 here. The bytes. Look at the raw bytes. There is no 0. And the 0 is important because a lot of bugs before, they are string copies. And the string copies stop at 0. If your shellcode has a 0 there, the string copy will only copy whatever before that 0, right? So let's say this string here, what we want to have is being sh. And because this is a C string, at the end of this string, we have to put a 0 there to make it a complete string. If there's only 7 bytes there, then you probably need to move a 0 in one of those places, right? And that 0, when you do a string copy, will not be copied. As you can see here we are putting this onto the stack, this string onto the stack. And at the end of this, we need to put a 0 there. But we're not directly pushing 0. Because if you have the instruction pushing 0, there will be a 0 in that. Instead, we're doing exclusive EAX, then push EAX. And that will probably be the first several full 5 characters, 5 bytes here, and there is no 0. Okay, that's the reason why we're doing that. This part is done. Okay, like I said, the reason we are doing the last 3 instruction is if that exe CVE is not successful, we want to clean it up, and technically it's not necessary. So that's actually what I have for the share-code part for this week. So I understand that the homework of last week might be a little bit more challenging than I wanted. So I want to ask how many of you got all the flags? Okay. So most of you who are here got the flags, but still there were like 10 people didn't submit the homework. So I don't know what happened there. So this week's homework will be a little bit easier. This homework, you basically just replicate what I showed you in the class. But next week's homework will be harder, as there will be some challenges I will not demo in the class. So today, we look at this piece of very simple shellcode. Next week, we are going to extend this shellcode a little bit to make it really work on the current system. We are going to look at 2 different shellcode. One is it will actually give us a shell, something like this, extend from this, from the 32-bit machine and the 64-bit machine. Another one is a shellcode that directly return the flag to us and do not give us a shell. So when it gives you a shell as an attacker, what you can do? If your goal is still to get the flag, then you can do cat flag, right? Or you can run arbitrary program there. Then the second shellcode we are doing is we will directly I will show you the assembly to directly read the flag and print it out using multiple system calls. The reason this piece of shellcode is not working is because I don't know if it's Linux or Ubuntu. It's probably Linux. I mean, when I say Linux, I mean the kernel. Made some slight change. So even if it's a set UID program, when you make the exe CVE call here, the system call here, so here we make a exe CVE call, and we are attacking a set UID program. Even if it's a set UID program, you directly make this system call like this. The new process created, or it's not really a new process, the replaced process will now inherit the root privilege directly. You need to make another system call before this. You need to make another set REUID system call to just kind of like tell the kernel again, okay, I need a root privilege, even if it's a set UID program. That's because of that, the shellcode that works will be longer than this. Before this, we will make another system call. Okay. So that's basically what I have for today. So I want to ask you guys, do you feel you need to go over the homework too? Since most of you here already got it. Everyone is good? Okay. Okay, so I guess we have a short class today. See you guys next week. I already posted the slides and also homework 2. Homework 3, yeah. This week homework will be a little bit easier. Give you guys a little bit break before next week. Okay. Start early with your homework. I saw many of you started very late, and for homework 2, 10 people didn't submit. I guess because they started late, they didn't even have time to ask me. So start early. Do not wait till the last minute.